All right, welcome to my optional video here. So this, honestly, if you want to know about Kriging, this is where you can find out about it. But if you are like, you know what, I'm good knowing it's a statistical service, that's okay, because that's all I really need you to know in this class. But I thought that I would give you a little bit of background as to what it is in this separate video so that you can go through, and if you want to try to mathematically model it, or if you wanted to if you are going on to the CBEPS exemptions, this is actually a really good background for you to look at, like 3D modeling and coordinate modeling. So it does help with that. So I'm going to go through it really fast. I know there's 41 slides in this, but I'll give you a few points on each slide. And then if you have any questions, feel free to ask. But again, this is optional. You have enough on your plate in this semester to so if you're like, hey, you know what, I'm going to skip it, that's okay. This is something you can go back to in a couple of years if you need to, because it's on YouTube, right? So so Kriging, so this is a type of geostatistical service. So what this really does is looking at the residuals, and it fits a model to the residuals after we have removed the actual trend. Okay, so this is looking at my final results, like my final accuracies, and saying this is how well your data represents, or your model represents this data. So in the end, though, what we're doing is we're really creating the error matrix, right? We have the residuals, but now we're modeling those residuals and saying this is so the true height of my points comes from a trend and the Kriging value. So we do have Fourier series. Why is this different? It just adds, like Fourier just kind of puts together everything. It doesn't just look at geostatistics, but it also doesn't look at the final residuals. It kind of takes everything into account, so it's kind of a little bit more global than Kriging. So that's what I mean, you can definitely look into it and research it more, and that's a really important question to pose because Fourier deals with the frequency domain, Kriging deals with statistics and geostatistics at that. So there's a couple disadvantages of doing deterministic methods, and that is all the other methods that we talked about in this class. So one of them is that we have no way to really say, hey, the points that we are choosing to estimate our values are actually the best ones, because we use sampling, right? So we go through and we choose an optimal sampling rate, and then we try to model based on that. So we're kind of, that's like one of the big things, is that we just don't know whether or not the points that we're using is good. And then the goodness of the prediction is to use elevations for an extra set of points, but that costs money to do. It's really rarely ever done in practice. So so that's one of the big disadvantages of deterministic stuff. And then, of course, there's no upfront way of choosing the best weighting parameters or the size and shape of neighborhood. This becomes something called heuristics, and that means trial and error. So a lot of the stuff that I deal with in my courses is a lot of trial and error. So to bring you into the world of geostatistical surfaces, there are two formats that Kriging uses, and I kind of listed these a little bit in local interpolation, and I said we're not going to be looking at them, but so this is why I'm kind of bringing it in here, because this is where I'm going to look at them, and not in much detail, just briefly. So there are two types. There's covariance and there's semivariance. Covariance. You can see that if we use a covariance model, the covariance decreases further away from the interpolation point. So this is how useful the reference points are. And so it's really measuring that. So this is like, okay, you know, how useful are the points around that data point that I'm looking for? And can I use them? Or what size and shape of area and neighborhood do I need? The semivariance is directly related to covariance, but it kind of looks opposite, so it increases with distance. It does plateau, though. So the plateau is what we call the sill, and the range or span is going from from the unknown point to that sill. location. So we need to figure out the actual function, like what is the mathematics behind it, and what's the model. So there's like 3 different kinds of models. The first one is an empirical model, also known as an experimental model, that uses my reference points that we have. We can also do model covariance. So we're looking at the experimental covariance function and choose a model that fits the best that way. So that could be like a polynomial. Usually it ends up becoming that. And then we also have the parameters of the model that we used, and we apply least squares adjustment. So there's, I guess it's like, these are more like steps. They're not really like fully separated out, but each component can take a while. So it's mathematically very complicated. So that is, those are kind of the major steps of figuring out covariance and semivariance functions. And so this is kind of what it looks like. So we have the experimental function, which is like the bumpy function. And then we have the model that we have created, which is nice and smooth. And we need, in order to do this and calculate these, we need to determine what it is at 0, like CD, right? So we have to figure out this covariance function is 0, and for every single distance that we're looking at along here. So now we're looking at the variance of elevations. So this EZ is my expectation of Z, which is a statistical calculation. So once the expectation of Z should equal 0 if you have removed the trend. And so mathematically we can calculate EZT times Z, and that's the expectation of these values of the Z's, the known Z's, and then we can calculate C0 at 1 over n times the sum of all the Z's squared, and that's going to give me my sigma squared, which is my variance. Then we have the covariance. So this is CD. So back here, we have the variance of the elevations, which is C naught. And then we have the covariance, which is CD. Again, looking at these expectations. So if you know how to calculate an expectation of Z, then there you go. You can do it there. But just to break it down and make it simple, we have 1 over ND, which is the number of the point pairs that are the distance, a certain distance from each other. So all those points up to that location, and then we multiply by each Z, I and J, of those 2 points, I and J. I and J cannot be equal in this case. Okay. So again, the covariance between, this is looking at CD, is the covariance between the elevations at the points, which are a distance apart. So in practice, we don't compute the covariance or semivariogram, which is those diagrams we were just showing, for every reference point, because that would take forever. And the distance itself is computed over the whole data set for certain distances, right? And then like it's set at different intervals, distance intervals. And then the covariance and semivariance are orientation specific, which adds to a lot more of the fun of that. So this is the Semivariogram, if you want to call it. That's with this range and SIL. So here's all your fun math right here that you would do to calculate this gamma. And this gamma is going to become like a weight later on. So your indices, number of points that are a distance apart, and that's how you calculate your sum. So there you go. 1 over 2, and then that's 2 over ND, or sorry, 1 over 2 times ND. And then you take the sum of ZI minus ZJ squared. So squaring is always a helpful thing for us to do, just because of the fact that it removes any negatives. And then we can always do a square root later. So semivariograms, we have 3 different versions. We have a linear semivariogram, which is just a straight line. We have a sphere, which is this solid line. And then we have exponential, which is the dotted line. You'll see exponential more often than sphere and linear, but mathematically the linear is much faster to calculate. And you can see gamma is on this side after you've calculated it based on the previous slide right here for every point. So the range or span in the semivariogram is the distance at which the semivariance will reach a plateau. So this is, and then the sill is when it reaches that plateau. And that's at the actual like the y value at that point. So the range or span, depending on the software that you're looking at, the distance beyond is the distance beyond which the elevations at the corresponding point pairs are not related anymore, right? So now I can actually say at this point my points don't matter anymore. So this is giving me that structure to be able to identify exactly at what point can I stop with calculating, especially local modeling. My local model, it gives me that structure to identify the size of my neighborhood. So here's my semivariogram. We've got my points, which is my experimental calculation, and then I've got the modeled calculation, which is this nice smooth black line. And then we can take a look at both of them, right? So we look at covariance and semivariance models, so C0 and CD. And then really we're looking at the gamma after we've, once we've calculated C0, and then we should have CD, so it will give us what, or sorry, blah, blah, blah. I'm talking too fast. So we're really trying to determine CD because we've calculated gamma and C0. So that we've done that math previously, now we can determine the math for CD. So there's my model, my covariance function right here. And C0 is this distance from here to the top here, right? Where does it start? And then using my semivariance, I can, basically you can almost draw a line across, but this is a different value, so don't get that confused. And if they are at the same spot, then they're directly related, right? Because now it should be from the sill point, and that's what's going to be measured there. And there's C0. So they should be the same. If they are, then we've done everything correctly. But if they're not, then that means that there's some more error in there. So the example deals with the empirical determination. So this means we actually have the values of the covariance function in the variogram. And so this is just a really quick example. So we have our points. They're kind of distributed 10 meters apart. They have elevations. So that's what 73 is. And we take the average elevation at 70.43. And then we go through and we remove that average elevation, and then we kind of, here's our values now, right? And then we can take our variance and we calculate C0 or C0. I keep on to call it C0, it's not C0, it's C0. And then we can go through and group them together based on distances and number of pairs that are within each of those distances. And then we have calculate CD, we can calculate gamma, tells us which pairs that fall within those values, and then the Z's as we go down. And then it goes all the way down to group 8, and then we do our empirical covariance. So, so this is the example of the numbers. So if you were to go out and plot these based on the numbers that you see in the covariance, right? So the covariance is here. Plot them out, that's what it looks like. It just kind of dies off, right? And then semivariance is pretty much the inverse of that, so it goes up. So now that we've determined covariance and Kriging, and again, you can go through the math and work through the numbers and give it a try with that example, if you're really interested. Then there is the interpolation using Kriging. So now we've got our semivariogram, the sill and range. Now, when we go to interpolate using Kriging, we need to use the elevations that we know and determine the semivariance function, like this. We need to choose a model, or the semivariance function that resembles the experimentally determined function, right? Then apply least squares, and then use the least to determine the least value to determine the interpolated height as well as its quality. So what's neat about kriging is that it's actually very orientation based. So we are, in this first step, when we're using them, we are going to look for our points, and we can look at all different quadrants. So there's a lot that goes into this. We've got a band going like north, northwest, northeast, east. We have a band width that goes across. There's an angle tolerance, like at what point is it considered a part of east? And then the lag step is our distance that we're calculating. And so our points depending on where they go. And so some key points with this one is that if the semivariograms are all the same, so that means in all directions they are all the same, then it is considered an isotropic process, which means it will return the same model every time. If the sills are the same and the ranges are different, then that's known as geometric anisotropy, which means that there's going to be some variation between each of the semivariograms in each direction. And then if the sills are completely different or the shapes are different, then this is zonal anisotropy. And so therefore each zone again has a different semivariogram. So there is some variation that can happen, and kriging allows us to identify that. Then, oops. I don't have my scan in there. Sorry. So then we're going to choose a semivariogram that represents the model. And if there is an anisotropy, then a 2D semivariogram can be fitted. So we just use 2 dimensions rather than 3. Just ignore the scan information. It's from a different textbook. So again, like I said, it's not super important, but just giving that next step. So there are 2 different kinds of kriging that I'm going to touch on really quickly in this lecture. An optional lecture, please remember that. The first one is the BLE, which is known as simple kriging. And so this is really the math. So what we're dealing with is a weighted matrix and the reference Z values. So you can see from the semivariogram, we have our gamma values based on our model of the reference, and this is 2 references, and then reference in the unknown point. Okay, so that's W. So it's looking at the inverse of that. Our interpolated height, again, looking at this, so W, which is our weight matrix, has my gamma values all the way around. Easy weight matrix, because all I'm doing is taking the semivariogram values and putting them in there. And then I have my gamma values, which are here, and there's just one to the point that I don't know, right? So these are the known, these are the unknown. To determine the quality, I find my C0 where the sill is located, and then I have my weight matrix and my semivariogram gamma value, and that provides me with that quality of the interpolated height. And then here, instead of, this is just the quality of the estimation, so instead of including the C0 or C0, I just calculate straight through with the weight and the semivariogram. So that's simple kriging. Believe it or not, that's the simple side. There is ordinary kriging, which is BLUE or blue. This is where we have an identity matrix and something called the Lagrange multiplier. So we use this to try to unbias our result, because there's always a bias in any kind of geostatistical surface, because we're like kind of choosing based on what we think is the best reference points. So this is trying to remove that bias and working through with that. So you can see again, the weight matrix times R is still the same setup. The only difference is that my gamma of ZR and P are impacted by gamma of the Z values times the weight plus this identity matrix and the Lagrange multiplier. But in this case, weight should equal 1. The sum of the weights need to equal 1. So again, once I implement that, that removes the unbiasedness, it fulfills the unbiasedness condition as it says, but it removes the bias that we put into our data sets. So mathematically, what does this look like? So we put it into our matrices. We have our gamma values, and then we put 1s along the side and 0 in the bottom corner. Okay. Then my weights calculated with my Lagrange multiplier here. And then we have, so all we're doing is adding condition, right? So if you think back to least squares adjustment last year, all I'm doing is applying a condition to all of my matrices to make sure that they are removing any of the biases that you might find within your matrices. So then in the end, you calculate your interpolated height, C0 minus the weight and the semivariogram information minus the Lagrange multiplier. And then the estimation error, you're just removing that C0 from that value. So there is an example here at the end of this PowerPoint. I'm not going to talk through it, but you are certainly welcome to take a look. So the idea is that I'm using this information here, and there's my data point, and I'm trying to figure out my Z of my data point. So I have all my coordinates, I have the distances, I create my semivariogram, which is a linear case in this situation. I create the semivariances from the model. I work through, this is BLE, so that I work through my simple Kriging. I get my sum of my weights, and then I can interpolate the height based on those values, and I get a value here. And then I can find out the estimation of the error, which is telling me it's about 5% of the interpolated height. So the weights do not sum up to 1, but it's close to 1, so that's okay. So if we do BLUE, which is adding in that conditional component of the 1s and the Lagrange multiplier, and then we go through and we see the interpolated height is 125 with a little bit less than 5% in error. So it does make a difference which kind you use. Obviously the BLUE does have a better error measure than the simple Kriging. So ordinary Kriging versus simple Kriging. But now the weights are equal to 1. So universal Kriging, this is another one. So it deals with the problem of looking at the trends, and not actually leaving the residuals as like randomly distributed. It kind of states it there in the third point. So we fit a local plane and we subtract it before doing the semivariogram. So it kind of helps provide some, I guess, rules, you would think, to the methodology. And this is really where there's low frequency or drift in your measurements. So like IMUs tend to have a drift, so that could be a problem when you're looking at LiDAR. So it can be very helpful, and that there are high residuals in the data set. So universal Kriging does actually help structure your results a little bit. But you do need to have a minimum of 5 points to be able, reference points to be able to do this, which usually we have. And then you get nice big matrices with lots of conditions that are included. So again, universal Kriging, you can also do by hand if you want. You can see the semivariogram information that is set here. You got your weights, you've got your X and Y values, and everything is kind of put together to figure out the answers. Again, I'm not asking you to do this. It just gives you a viewpoint that Kriging deals with covariances, semivariograms, semivariances. It deals with weightings. You can put conditions into the matrices to try to remove bias, and then it calculates errors of your model, and there's statistical errors because it's a geostatistical surface. So I know I went through this very fast. I went through 41 slides in 25 minutes. So again, this is optional. You're welcome to take a look at it if you like. Nothing in here is going to be examined on, but if you are interested, and just as a quick summary, talked about what covariances are, what semivariances are, what a semivariogram is. We talked about what simple Kriging is and what ordinary Kriging is, and then right now we're looking and finishing up on universal Kriging, what that looks like in the end. So I covered lots, probably talked really fast. This was only for your information if you need to come back to it in the future, maybe for like a CBEPS exemption or something. And so I hope you enjoyed this one, but don't stress about it because it is not on the exam.